Okay, this is a problem that presents itself as a candidate for integration by decomposition into partial fractions. And what tells me that is that the integrand is a polynomial divided by a polynomial. And in the first step in problems like these is to make sure that you can't simplify the integrand any further. For example, if the numerator had a degree higher than the denominator, I would want to start with long division of polynomials. That's not the case here, so I can dive right into the decomposition part. And decomposition into partial fractions means first finding a factored form of the denominator. So I'm going to start with that. X cubed minus x squared plus 9x minus 9. If I use factoring by grouping, I get a common factor of x squared and then x minus 1, and a common factor of 9 and then x minus 1. So now I have a common factor of x minus 1, and when I factor that out, the terms that remain are x squared and 9. So the denominator factors like this. All right, so that means that I can write this, this fraction, if you will, this rational expression, as 4x squared plus 2x, plus 2x plus 34 over x minus 1 times x squared plus 9. And partial fraction decomposition tells me that I can write this as a over the linear factor. Let me tidy that up just a little bit. Plus my quadratic factor here is an irreducible quadratic factor. If I could factor that further, I would. Creating just linear factors makes a much simpler problem to work with. But in the case that I have irreducible quadratic factors, my numerator is not just a single constant like the a in the first term here, but it is in fact a linear factor, bx plus c. Okay, so now that I've got this in this form, what it is that I'm saying is that the left-hand side here equals the right-hand side, and I need to find another way to try to express that. One thing to note is that on the left-hand side, I still have a cubic. It's in factored form, but I have a cubic. And on the right-hand side, I have the sum of one term over a linear and the other over a quadratic. So if I want these to actually be, if I want to be able to compare these in any realistic way, I'm going to want the denominators to be the same. So I've done the decomposition now, but I need to kind of put things back to a certain extent so that I can actually figure out what the values of A, B, and C are. So what I'm going to do now is rewrite the left-hand side. And I'm going to try to find a way to write the right-hand side so that I can combine the terms in the numerator so the denominators are actually the same on the left and the right-hand side. So I have a over x minus 1, but to get the denominator so that it's x minus 1 times x squared plus 9, I'm going to multiply first fraction by x squared plus 9 over x squared plus 9. And then I have a plus, and then I'm going to multiply my second fraction, which only has in its denominator an x squared plus 9. I'm going to multiply that by x minus 1 over x minus 1. And now I can rewrite the right-hand side as a times x squared plus 9 plus bx plus c times x minus 1 all over x minus 1 times x squared plus 9. And the benefit of this, if this is still equal to the left-hand side here, is that if these truly are equal, and they are because I've only done basic legal algebraic moves on the right-hand side, if the left-hand side and the right-hand side are identical, if they're equal, and the denominators are equal, then the numerators must also be equal. So I can now write 4x squared plus 2x plus 34 has to equal a times x squared plus 9 plus bx plus c times x minus 1. And then I'll carry on here. That means that ax squared, I'm distributing, plus 9a plus bx squared minus bx plus cx minus c. And then what I'm going to do is combine like terms. I have ax plus bx, and I'm just going to go ahead and factor that x squared out. Sorry, ax squared plus bx squared, and I'll factor the x squared out. So I have a plus b x squared plus, and I have a negative b plus c. I'm just going to write that as negative b plus c. I like my terms or my terms in alphabetical order, factoring out the x. And what I have left then is 9a minus c. And I'll put that in parentheses too. What that gives me is a coefficient of x squared, a coefficient of x, and a constant term. And for the left-hand side and the right-hand side of this equation to continue to be equal, the coefficient of x squared has to be equal to the coefficient of x squared, the coefficient of x to the coefficient x, and the constants have to be equal as well. And so that gives me then a system of equations. I can say, I'm going to have to go up here a bit to the left. I think I'll try to leave myself some space. This gives me that a plus b has to equal 4. Negative b plus c has to equal 2. And 9a minus c equals 34. And so this is a system of 3 equations and 3 unknowns. I would argue that this is not a class in linear algebra. And so at this point, I would not penalize a student for doing this part of a problem like this on a calculator. This is a fairly simple system. So I'm going to go ahead and finish it out by hand, but it's not necessarily strictly, it's not strictly speaking necessary to do this by hand. This is not the focus of a course in integral calculus. So I'm going to start by adding these 2 lines together. The reason I'm doing that is I've noticed that they're already set up so that if I add them together, there will be no b term when I'm done, and that's already the case in the 3rd line, the other line down here. So I'm going to try to produce a new equation that only has a's and c's in it, and then I'll use the 3rd equation, which already only has a's and c's in it. I'll combine them. So a plus b minus b plus c equals 4 plus 2, and that's probably not the best place to put that. Let me just rewrite it. A plus b minus b plus c equals 4 plus 2. And the 3rd equation, 9a minus c equals 34. And those are set up for a term to cancel. So I'll just add these together. I get 10a equals 40. And solving for a, if I divide both sides by 10, I get a equals 4. So I now know what the a is in this fraction. A is going to be 4. And if I know a, I can use it to find b, because now I know that 4 plus b equals 4. So that means b must be 0. So I have a equals 4 and b equals 0. And since a equals 4, I can figure out what c is as well. I have 9 times a, which is 9 times 4, minus c, good grief, minus c equals 34. That's 36 minus c equals 34. Subtracting 36 from both sides, I get negative c equals negative 2. That means positive c must be equal to positive 2. And I have the values of all three of my coefficient variables. So now I can rewrite this integral. I'm going to have this integral here is equal to the integral of a, which I now know to be 4, over x minus 1, plus bx plus c, which I know is 0x plus 2, so I'm just going to write it as 2, over x squared plus 9 dx. And hopefully you recognize by now that this is this first term here is once you integrate, is a natural log. I'm going to have the natural log of x minus 1. And because it's not the purpose of this video to talk about the techniques for integrating a term like this, I'm just going to resort to the formula, if you will, the integral from the table in the back of the book, or wherever you might be sourcing that information. This is the integral 2 over x squared plus 9 is the same as 2 times the integral of 1 over x squared plus 9. And the integral of 1 over x squared plus 9 is 1/3 arctan of x over 3. Okay, I'm going to tidy this up just a little bit more. I have the ln of x minus 1 plus 2/3, just multiplying here, the arctan of x over 3, and then of course plus c, because this was an indefinite integral. Okay, so here's my final answer for this. The goal of this video really was not necessarily to get to the final answer, but to show you how to set up the decomposition into partial fractions. And that was this step right here. And the key, one of the things that you might be struggling with is it's kind of this step right here, where you may be asked, depending on the situation, you may be asked to write this numerator out kind of in semi-factored form. And that's a kind of a missing step for a lot of people. So I hope this has helped, and I'll see you on the next video.
Let's talk about writing proofs in trigonometry. Proofs are how mathematicians talk to each other. Well, not really, but in a way they are how we share fundamental mathematical ideas that, once established, can be used over and over. After something has been proved, it is unquestionable, and anyone can use the result to do bigger and harder problems without first having to stop to establish each piece. The trigonometric identity sine squared plus cosine squared equals 1 should be familiar to you and serves as a good example of why proofs are important. If I am asked to demonstrate that 1 plus cotangent squared equals cosecant squared, I can start with the known identity sine squared plus cosine squared equals 1, because that one has already been established. Imagine if you had to prove that one first each time you wanted to use it. Something you should know before we start is that when you see someone demonstrate any kind of proof, chances are that they know exactly what each next line is going to look like. They have probably worked out the steps beforehand and are just showing you what those steps are. In reality, writing proofs is much messier than that. In another video, I'll show you what I mean by working through a proof I haven't prepared in advance. There are multiple ways to write proofs. In this video, I'll show you how to prove a trigonometric identity the way I require my students to do it. Your instructor might want you to do it a different way. If no particular method is dictated, then this technique will almost always work. Since this is the first time for most students that they've had to write a proof on their own, I feel it's best to give you one strategy so that you can focus on the logic and the importance of the details. As a student, I always felt like writing proofs was some mysterious skill that you had to figure out on your own. That's because there are so many different ways to do it. This is just one. but it is highly structured and should serve you well in most cases. Let's prove the identity tan theta over secant theta equals sine of theta. This is a very easy proof, but it will demonstrate the process. Then we'll do some harder ones so that you have some other models. Begin by writing out what it is you're going to prove. Tangent of theta over secant of theta equals sine of theta. This is a statement that you are making a claim and that what follows will demonstrate that your claim is true. Some mathematicians and some instructors may have you write required to prove or RTP to the left of this statement. That helps establish that it is a claim rather than an assumption, and that there is more to follow the initial statement. Adding that is not wrong, so I'll leave it. Now we'll select one side of the identity and show that it is equivalent to the other side. This is where a lot of people get lost. Since you are trying to prove that the two sides are equal, the one thing you must never do is say that they are equal. You have to demonstrate that they are equal using logic and algebra. The side that you choose is up to you, but it is usually easier to do the proof if you start with the more complex looking side. That's because there's more on that side to work with. So we'll begin with that. I will choose the left-hand side of this identity and show that it is equivalent to the right-hand side. Since I am using this to communicate with others, even if it is just my instructor, I must be very clear about each thing I write and what role it plays in the process. To that end, you must write LHS, which stands for left-hand side, at the beginning of your proof. Some instructors may not require this step, but I do. Next to LHS, I will state what the left-hand side is, namely tangent of theta over secant of theta. I note that these are equal since it is simply a statement of fact that the left-hand side of my identity, which was given to me to prove, is in fact tangent of theta over secant of theta. The rest is up to me. I have to show that this expression is equal to another expression, which is equal to a third, and so on, until I have found a way to write it so that it looks like the right-hand side. To do that, I'm going to use a series of trigonometric identities that have already been proved, or which I've been told that I can use. For example, algebraically, I can write tangent of theta over secant of theta as tangent of theta times 1 over secant of theta. All I've done is use a little bit of algebra to write this expression as a product instead of a quotient. Now I'll use some trigonometric identities. One is that tangent of theta can be written as sine of theta over cosine of theta. Another is that secant of theta is 1 over cosine. More importantly for me, 1 over secant is cosine. So 1 over secant of theta can be written as cosine of theta. Now we can make the observation that the cosines can be canceled. After that, when I tidy up my work, I just have sine of theta. Well, this is exactly what I was trying to prove, that tangent of theta over secant of theta was equal to the sine of theta. And I've done that now, not by making any assumptions, but by using some previous results and showing algebraically and logically that the expression tangent of theta over secant of theta is equivalent to the expression the sine of theta. There's one last step here. At the beginning, I wrote LHS for left-hand side. At the end, I'm going to write that this is equal to RHS, which stands for right-hand side. So ultimately, what I've shown is that the left-hand side is equal to the right-hand side. And there are several steps in between, but each one is equal to the one before. And that's the sort of thread of logic that we want to use in these. As I said before, there are multiple other ways to write proofs, but trigonometric proofs are easy in a way in that you can always use this strategy to show one side of your identity is equal to, algebraically, some other expression. And then you can just continue playing with those expressions algebraically and using trigonometric identities that you already know to rewrite the expression until it looks the way you need it to look. It sounds simple, and sometimes it is, and sometimes it's more complex. Let's try another one so that you can see what I mean. My instructions might look something like this. Verify the identity cotangent of x times secant of x all over cosecant of x equals 1. The left-hand side looks considerably more complex, so I will start with that side again and show that it is equivalent to the right-hand side by demonstrating several intermediate algebraic steps. We have to remember that we are required to prove, although for some people that step may be optional, we are required to prove that cotangent of x times secant of x all over cosecant of x is equal to 1. And then when we begin, you may also want to write proof to show that you're about to prove this statement. Now let's write left-hand side equals, and we'll rewrite the left-hand side. Cotangent of x times secant of x all over cosecant of x. Notice that I have not done anything in this step to change the left-hand side. I have not done my first algebraic logical step. I have simply rewritten the left-hand side. This is important because you're establishing a starting point. It's really tempting, especially with ones that seem like they're going to be easy, to dive in and start rewriting things. But your first step should always be just to rewrite one side or the other of the identity. Now that I've done that, I can start playing around with it. I'm going to start the way I did the last time, by writing this quotient as the product of the numerator, cotangent of x, times the secant of x, times 1 over the denominator, cosecant of x. I've simply changed the form that this expression takes. Now I can start playing around with each of the three pieces here. The cotangent of x can be written as cosine of x over sine of x. Secant of x can be written as 1 over cosine of x. And 1 over cosecant of x is sine of x. Now I can see that sine of x over sine of x will cancel, and cosine of x over cosine of x will cancel. And everything has canceled now, and the result, therefore, is 1. Well, that's exactly what I wanted. The right-hand side of the identity that I'm trying to prove is 1. So at this point, I can just say that that equals the right-hand side. And I'm done. These two examples were very similar in the strategy used. In the next video, I'll discuss a few other strategies, and we'll do some examples using those.